Okay, welcome in everyone to my channel. I am Professor L, and this is a stream for math help. So if anyone is out there watching and wants to post a question, math related, that is, in the chat, then that is the idea behind this project that I'm doing here. And in the meantime, I'm going to be just hanging out informally, trying to explain random topics on my board. And today, I have decided to talk a little bit about rational functions. And I'm going to graph a rational function. And so I wanted to kind of backtrack and I'll just get right into it, I guess. I hope everyone's doing well. And so what I did was I did what a lot of people do, and so I want to kind of use it as a teaching moment. And recall yesterday I was holding up my ruler trying to find some symmetry here about the origin. And what I was doing was I was confusing an inverse with a reciprocal. And while the reciprocal is a multiplicative inverse, it's not quite the actual inverse. And so it's not gonna, you might find some symmetry about the origin, but it's not gonna follow that exact symmetry about the identity function line unless it's an actual inverse. And a function's inverse results in another function entirely. A function's reciprocal is just found by taking that function and putting it over the quantity 1. So, or under the quantity 1. And I'll kind of show you what I'm talking about here because I know I just kind of said a lot. So I kept confusing that yesterday, and it was bugging me after I reviewed my stream. So I am trying to review these streams and just because this is actually, just as important for me to grow in this platform as it is for me to be effective and try to help in helping students eventually what I want to do here. So I just wanted to say that I thought it was worth saying that reciprocals are multiplicative inverses, but they're not actual functional inverses. So hopefully after I spend some time working with these reciprocal functions today, what I'm going to do is I'm going to start the topic of rational functions, which would be backtracking from trigonometry. It's back in college algebra land where we talk about rational functions. And so it would be before trig. So it is kind of backtracking a little bit, but I eventually want to get back to the trig and do transformations on the trigonomeric functions. But I'm not there yet, and I'm researching that and practicing that, and hopefully after I get done backtracking on rational functions and polynomials, I can be well versed in transforming the graphs of the trigonomeric functions, which is a kind of an end goal. So graphing rational functions is what I want to title today. So say graphing rational functions. And a rational function, okay, it's math terminology for basically we're saying a rational number. Okay, not thinking and working at the same time. Rational numbers basically are in the form of P over Q. So it's essentially explaining all of the fractions. So P and Q are integers. And so it's all the fractions. Okay. So when we're talking about rational functions, what we're talking about are polynomials. So we have P of X over Q of X, where P of X and Q of X are polynomials. Okay. So I'm going to try to, in a nutshell, basically explain rational functions. And so we have what are polynomials? This word, and poly just means many. So it's essentially many terms. Nomials would be terms. So, for example, first, and they're named by the number of, or the highest degree of exponents. So, like, for example, a first degree would be all your linear functions. Okay. What do I mean by linear? I mean y equals x. And let's see, what it would be y equals x, also y equals a, and x equals b. And then you'd have second degree, which would be your quadratics. And it's named by the exponent. Notice all of these, you're only having x to the first power. So another one would be like if you had y equals, let's just do 2x plus 5. And then second degree is your quadratics. And then, for example, you would have, and we won't go too far into this, but you'd have y equals x squared plus 1, where it's a second degree, and you'll have a term that is raised to the second power. So that would, and then so on and so forth. The third degree, as expected in the pattern, would be your cubics, where you'll have a third degree term, x to the third plus 5. And again, you're looking at the degree of your exponent here for these. So you've got first degree would be your linear function, which would be leading to your lines, and then your straight lines, and then you'd have your quadratics would be your U-shaped, and then your cubics. So let's go ahead and sketch some graphs in here. So like 2x would be rise 2, and so we have an intercept at 5, and then you're rising 2 and running 1. So you have this function going on. For your square graph here, This is centered at the origin, and you have a shift up 1 for your quadratic. Your cubic graph is will be up 5. But what it's doing is it's having symmetry about the origin. So they all have their own behaviors according to the degree of their exponent. And then in the theory, you learn that even numbered exponents are even functions, and they have symmetry about the y-axis. And then you learn about your odd functions, and they have symmetry about the origin. And so it depends on the term for polynomials. This is specifically for polynomial functions. Okay, and we might get back into that. But when you're taking a rational function, essentially you're just taking two polynomials and dividing them. And there is theory involved in sketching the graphs, and they do get pretty complicated. Today, what I'm going to do is I'm going to specifically, I'm going to erase some of this. I'll keep some of it up. And then did I erase that one? We'll put this one back in here. All right, so we have basically what I was going to do today is just focus on the linear function, the identity function. It's called the, hang on. Okay, it's a first degree polynomial, and it's y equals x. So every value y is going to equal x. And I'll go ahead and sketch my graph here. Let's see if we can. And I've talked a little bit about this identity function, but so we'll sketch our little Cartesian coordinate system here. And then recall the identity function, every value of y equals x. So if I want to pick, we'll just pick some points here. We'll pick 0, -1, 2, -3, -4. And we'll have a nice symmetrical graph. 1, 2, 3, 4. And then we'll do the same here. 1, 2, 3, 4, -1, -2, -3, -4. All right, so all we're going to do is we're just going to pick values in our domain, and we're going to sketch the graph of this identity function. So we'll just say -4. And actually, to save room, we're going to go ahead and not have a table for the identity function. We can just plot points, because if y equals x, then I can just say when x is 1, I have 1. When x is 2, I have 2. When x is 3, I have 3. And basically, we're going to get a perfect diagonal through the first and the third quadrants. So I've got 2 and 2, 3 and 3. The dots just help me because I don't have a grid up here, so I want to be able to sketch a pretty good one. Also, I'm going to dash this one because what we're going to do is we're actually going to sketch the reciprocal to the identity function. So the reciprocal function is found by reciprocating the identity function. So the reciprocal would be y equals 1 over x. Okay. And this is the one that we're actually going to work on today. So you find the identity function and then you reciprocate it, and then you get the reciprocal function. And what that does is it creates a situation where you'll have values where your denominator goes to 0. So we'll have to talk about vertical asymptotes. So when x cannot equal 0. So you have a vertical asymptote at x equals 0. So we have when x is 0 here, this is the y-axis here. There's an asymptote here. Okay. And then there are also horizontal asymptotes. And the rule for finding horizontal asymptotes is this. If, so it's a case, there's 3 cases. So case 1, and you'll look at the numerator and the denominator. If the numerator is 1 degree less than your horizontal asymptote is at y equals 0. The second case would be if they're equal degree, then you would look at the coefficients. And if the denominator is less degree, 1 degree less, you have an oblique asymptote. So we'll talk more about that later. But for now, since the numerator has 1 degree less than the denominator, technically it does, because if you look at it, y equals 1 over x. It's that hidden 1. That's x to the 0, and that's x to the first. And remember, x to the 0 is the value 1, so it's just hidden off. So even though this doesn't look like it has a less degree because it's just the number 1, technically it does, because of this caveat right here. So we have a horizontal asymptote at y equals 0, and we also have a vertical asymptote at x when x is 0. So when x is 0, so we have this graph that's basically, I guess we could partition each, dash both of these, because this is where the asymptote is. It's on the x and y axis here for this function. See what that looks like, dashing. So what we're going to do is we're going to go ahead and plot our points for this function right here. And we're going to use these same values here. So we'll say x is -4. And I'll plug it into our function. We have y equals 1 over -4. And then when x is -3, we have y is 1 over -3. And then so on and so forth. So we have x is -2. We're going to have y is 1 over -2, which is 1/2. So 1/4 is 0.25. So out here we have, if this is 1, the 0.25 would be about right here. So let's see if I can draw this in here. We have a dot here. -3 would be at 1/3. So if that's half, 1/3 is slightly more. We got that one covering -3. -2, it's at 1/2. So we're right, looks like it's right there. And then -1, we're at 1 over -1, which is -1. So that's a point on the graph, 1, -1. Right there. They're going to share that point in common. And then we got 0 undefined. And then 1, 1 is going to be on there. So we've got this sort of thing happening. And then what happens at, we'll have to find some of these halfway points. So this function's doing is it's bending towards its asymptotes here. Because if we try to find, let's just try to find a couple more of these points in here before we get to 0. So say I want to find out what's going on at -1/2. Well, when I try to plug in, let's plug it in here. Y equals 1 over -1/2. Then that's 1 over 1 times -2 over 1. So that's actually putting me at -2 now, here. And if I try to plug in, let's try to do some more of these points. What about, see, a little bit further over from 1/2 would be 1/3, -1/3. And it'd be the same situation here where you're plugging in y equals 1 over -1/3. So that's going to be 1 over 1 times -3 over 1. That's going to be a -3. -3 is on there. And then the same for 4. It's going to be 1/4. -1/4 is going to be -4 for y. So we have this sort of thing going on for our rational function. All right. And then you get to 0 and it's undefined. Let's continue our table here. X comma y. So we found 0 was undefined because when you plug in 0, you got 1 over 0, which is undef. But if you go over here to make a perfectly symmetrical graph and you want to go ahead and plot in some of these positive values, you'll start with positive 1/4. And then when you reciprocate that, you get y equals 1 over 1/4, which equals 4. So at 1/4, we're all the way up here at 4. Okay. And then 1/3 will be the same thing. You're at 3. 1/2, you'll be at 2. And then you got 1 comma 1. And then we'll plug in a couple more here. X comma y. will go 2 is 1/2, 3 is 1/3, and 4 will be 1/4. So we've got 2 is 1/2, 3 is 1/3, and 4 is 1/4. So we've got this sort of thing going on. Okay. And while you can see some kind of symmetry here about the identity function, it's not the inverse function, if that makes any sense. It's the multiplicative inverse, so it's going to have some symmetry, but it's not the actual inverse. I guess this one, let's see, this one would technically pass the vertical and horizontal line test. Okay, so anyway, introduction to rational functions. So basically, these also get pretty complicated. And so let's see. If go ahead and erase this. So go back. So, for example, horizontal asymptotes. So you have case 1, okay, and the numerator is it's 1 degree less. Case 2, they're equal degree. And then case 3 would be your obliques. The denominator would be 1 less. One degree less than the numerator. So let's see. Let me just see if I can come up with some examples real quick off the top of my head. So if the numerator was 1 degree less, we already saw an example of that here. But it would be like this: 2x, so y equals 2x over 3x squared plus 1. I am not good at coming up with examples. This is an example. Do you see how it's first degree here and second degree here? So your asymptote is going to be at y equals 0. Okay. If they're equal degree, let's see what I have written down. So y equals 2x squared over, what was it, 3x squared plus 1. Then your asymptote is going to be, you'll look at your denominators here, 2/3. Okay, y equals 2/3 would be your asymptote. And then if it's your denominator is 1 degree less, I thought I had one written down for this one. Here. If your denominator is 1 degree less, then I wrote this one. You have y equals x squared minus 9 divided by x minus 4. Wait, that one was not a good example, was it? Oh yeah, okay, it's fine. Because what happens is that there's an oblique. And what oblique means is slanted. So I'll just put slanted. Okay. And what happens is you have to use synthetic division to find it. There's not an E in there. Synthetic division. And so let's try to go ahead and do it. All right, so it's a shorthand from long division. So you can either use the long division method, so we'll say synthetic division, or long division. And what I really want to do is practice this. So we'll find it real quick. So this is, what you got to do is you take your denominator. What you're doing is you're dividing these polynomials. So let's see, x minus 4. We're going to divide it into x squared plus 0x minus 9. So you have to put the placeholder in here. So let's see if I can remember how to do it. So we'll first take x and divide by x squared. Let's see. So we'll say x squared divided by x. That equals x. And let me erase that and put it over here. So we'll say x times x minus 4. And that's x squared minus 4x. So we're going to say x squared minus 4x. And we're subtracting, so we've got to change sign. Because you're actually subtracting that. So what you do is you have to multiply everything by a negative. So that term cancels out. You put x here, and then you add. So that's going to be plus 4x, and then you bring down the 9. So it's 4x minus 9. And then when you divide 4x by x, you just get 4. So that's going to be plus 4. And then you say 4 times x minus 4. And that's going to give you 4x minus 16. 4x minus 16. And then you're going to subtract. So you change the sign. It's going to give you 0. And then, let's see, 16 and 9. But the remainder doesn't really matter. You're finding your line for your asymptote. So 16 from 9 is 7. 16, hang on. 10 from 9 would be 6. That's, yeah, 7. That's 7. So you have a remainder of 7, but this is how you find your line. So your oblique asymptote for this would be y equals x plus 4. And in reality, if we wanted to, we could go ahead and try to sketch the graph of this one here. But I've already been talking for 30 minutes, and so I don't see anything in the chat yet. That's fine. I am really, it's really hard for me to learn something new. And I struggle with change personally. So I am fine with not having a whole lot of chat and to manage at first, especially trying to just get comfortable explaining and trying to talk to a camera is hard. So this is good for me. Anyway, we can go ahead and sketch the graph in here if you want to. Do I want to? Or do I want to just stop there? All right, so what I might do is go ahead and stop there since I'm 35 minutes in, and I will probably continue this subject tomorrow where maybe sketch a couple more of these rational functions. So, and we'll try to go through some of this again in the process. I'll try to find a pretty good one. So. Wait a second, I have this, so I'm gonna write this in here, so in case my chat goes away. Graphing rationals. So let me write this in here. Y equals 1 over x minus 1 plus 2. Well, if we graph this one, now I'm going to have to explain the transformations in the graph. So, let's see. I just want to erase half of the board to write this in here. So we have this function, y equals 1 over x minus 1 plus 2. And what this is a transformation in the graph of this graph specifically. So all it is you're taking all of these points and you're making some shifts to them. So you could actually sketch this one a number of ways. You could evaluate it, or you could sketch the graph of its parent function, which would be the reciprocal function, and just shift the points. So we already have our table of values. So all we have to do is literally move every point up 2 and to the right one. Because here's your horizontal shift and here's your vertical shift. So if we could make another table here of values. Skip this over a little bit. We have x comma y. And so we'll pick the same values in the domain. We'll say -4, -3, -2, -1. Let's move that one over. And we've got 1, 2, 3, 4. Yeah, 1, 2, 3, 4. -1, -2. All right, so if we started out with -4, all we're doing is plugging in. So we'll go ahead and make a list here. -4, -3, -2, 0. And we'll go ahead and do some of these fractions here. -1/2, -1/3, and -1/4. If we take this point right here, -1/4, we could just shift it up 2, 1, 2, and then we're going to the right 1 degree. So instead of negative 1/4, it's 1/4. Let's see, maybe plus. We could physically shift those points up and over, or we could just plug in -4 into this and evaluate it. I might want to kind of just do that. So we'll say y equals 1 over -4 minus 1 plus 2. And we got y equals 1 over, looks like that's 1, -1/5 plus 2. And then, well, you plug in your calculator or you would just add your fractions. We'll go ahead and just add them. So we've got negative, let's see, -5. So it's gonna be 1. And then, let's see, 5 times 2 is 10. So that'd be plus 10. So it looks like I've got 11 over -5 for my first term. So we've got, and let's just see where this -11 divided by 5. That's almost 2. -2. So we've got at -4 here. We're all the way up here, almost. Wait, -2. Yeah, right here. -4, -2, if I calculated that correctly. Okay. And then this would be really ugly without a calculator, but that's okay. So then we would just, I'm gonna erase this and we'll try to find another point in the graph. And it might be easier to shift it. It's your choice. If you're familiar with the transformations, you could just move those points. But if you're not, then what you're gonna want to do is just plug in. So let's see what the function's doing at -3. So we'll plug in 1 over -3 minus 1 plus 2. So we've got y equals 1 over, see, that's -4 plus 2. Get your common denominator, which would be 4. And then, so that's going to be negative, that'll just be 1. And then 2 over 1. So we've got 4 goes, that's -8. So that's going to be -7 over -4. See, that's almost, see, I'm going to use my calculator because that's less than 2 now. I'm getting my calculator out. Okay, so that's really close to positive. This was a positive point. I messed up. My goodness, now my nerves are getting me. Okay, so 1 over. That other point was, this was positive 11/5 because 2 negatives make a positive, and this would be positive 7/4. And my calculator battery crashed on me just now too. So, all right. I'll go ahead and do a couple of more, and then I'm probably gonna go ahead and stop. Okay. So we've got y equals, we're gonna plug in -2. So that's 1 over -2 minus 1 plus 2. So that's going to be 1 over -3 plus 2. And the 2 is greater, so I should have a positive result when I add these two. So I'm really just subtracting 2. All right, so we've got our common denominator would be -3. So we've got 1, and then it's going to be plus or minus. So -3 times 1 is 3, so it's going to be -6. All right, so then that's going to be -5 over -3. So that's real close. That's right under 2. So it's going to be a positive. So we've got 5/3, and then 0 would be a lot easier number to evaluate. When you plug in 0, you just get 1 over -1, which is -1, plus 2 would be 1. All right, let's go ahead and plot some of these points and see where we're at. So we've got -4 and 11/5. That's slightly bigger than 2. Oh yeah, also, we need to go ahead and figure out where the asymptote is. You have to actually add this. Okay, so since it's not in the form, the asymptote isn't going to be at x equals +1, because that's not where necessarily this function is seeing 0 because of the 2 shift. So you'd have to actually add these terms. So you'd have to say 2 over 1 plus x. All right, this is making me remember this stuff. So here in a second, after I graph these points, we're going to go back and try and find the asymptote, and then I'll probably stop. Okay, so where are we at? 11/5. 7/4 is, so that's slightly more than 2. And now this one is slightly less than 2. So it's getting a little bit smaller here. And then this one, it's right here, is 5/3. So 3 times 2 would be 6. So it's just a little bit more. And then we've got 0, 1 here. So it looks like -1/2. Let's go back up here and try and find the asymptote. It looks like what this one is doing is it's going to come over here and cross down, is what I'm suspecting. But I'm going to go ahead and erase some of this, I guess. I definitely want to keep this graph up because this identity function, we have to write the right. This is y equals, erase this one because I already rewrote it over here. This is y equals 1 over x. But this one, if I wanted to find the, if I want to say, 1 over x minus 1 plus 2 over 1. If I want to add these fractions, what I got to do is I'm going to get a common denominator of x minus 1. So I'm going to have 1 plus 2 times x minus 1, because I'm just going to multiply what's in the denominator here to get common denominators. Does that make sense? Kind of. So, well, it'll still work out that it's still, okay. So then this becomes 1 plus 2x minus 2 over x minus 1. So this is the real function that you're graphing. And this is going to be 2x minus 2 over x minus 1. So this is everything I'm remembering about rational functions. I love this because I actually have a real problem to work with. Okay, so this is in essence here what you're graphing. I know that this is its transform state, but they're equivalent. Except for it's minus 1 here. 2x minus 1. There we go. Since they're of equal degree, then you're gonna have, so it looks like we have our horizontal asymptote at, so that's gonna be y equals 2. This is our horizontal. So at y equals 2 here, there is a horizontal asymptote. I'm gonna erase these points. I'll skip that over just a little. Okay, so here is the horizontal asymptote for that function. And then you're also having a vertical asymptote at +1, looks like. So your VA is found where your denominator is going to go to 0. So you have x minus 1 equals 0. So x is going to equal 1. Some sort of vertical here. All right. So again, it's just this graph here. If you could imagine that it's just been up. So here's 1. So we had our asymptotes at 0, 0. Now we have it, we're shifting going up 2 and over 1 for that new intersection. So it's all these points. It's the same behavior of that graph. It's just bending towards those asymptotes here. So we know the general direction of this graph. So we had found this point, this point, this point, and then it's supposed to be right here at 0, 1 would be where it's bending here. There we go. Okay, so now we're there. If that's any better. All right, so we didn't really look at these points here, but we can if you want to. We've got negative, let's see, where do we go to? 0. We can back up in here and go find some more of those little points to see what's going on here. After it hits 0, we could go and find out what's going on at +1. Let's do that instead, since we know that these points are going to be pointless. Oh, sorry. That was a silly pun. All right, so let's go ahead and see when x is 1. This function, oh yeah, that's our asymptote. We found that, so that's undefined. And then when x is, let's find out. Okay, so when x is 2, it's going to be up here, probably. So let's go, instead of 1, we'll do 1/2, +1/2. And plug in to our function. So we've got y equals 1 over 1/2 minus 1. I think I would rather actually use this one. So 2 times 1/2 minus 1 over 1 times 1/2 minus 1. So 2 times 1/2 is 1. Oh, look there. 1 minus 1 is 0. 0 divided by whatever. So 1/2, 0.1, that's negative 1/2, but still, it's just 0. Because you can divide 0 by a number. So I found my other 0. So that's where it's crossing. So y at 1/2 y. See what x is 1/2 y is 0 right there. That's telling you where. So that's your when x is 1/2 y is 0. Okay. So, and then let's go ahead and do, well, how about, we'll do a fourth, 1/4. We'll do a third and then a fourth. So we've got y equals 2 times 1/3 minus 1 over, that's just x. So that's going to be 1/3 minus 1/3 minus 1. Okay. Well, anyway, that was really fun. So that's going to be 2/3 minus 1 over 1/3 minus 1. It has been a while since I've done math. I'm exhausted, but that was really fun. So I appreciate the problem. Hopefully it's helping. So we're going to get a common denominator here. We're dividing mixed compound fractions. I love this. So the common denominator is 3. So that's going to be 2 and then minus 3 divided by, so that's going to be 1 minus 3 over 3. So that's going to be -1 over 3 divided by -2 over 3. Ooh, that is ugly. We'll finish it. So -1/3 times -3 over 2. And that's going to give me a positive 1/2. So we've got 1/3, 1/2 on there. Is that right? Let me see. So 1/3. Yeah, that's probably on there. It's probably right there. Good. This one's an interesting one. I like it. I'm probably going to graph a much better pretty picture and practice, and then I'll work on it and I'll start with it tomorrow. Thank you so much. Oh, what does it say? What are you saying? Okay, how to state the asymptotes. All right, for this graph right here, you're going to let me erase all of this and start fresh. So for the asymptotes, if you're wanting to state asymptotes for this graph right here, you're going to have to change it to its polynomial form. Okay, so that's +2. Like I did before, where you're just going to get this under one denominator, x minus 1. So the first term is not going to change. You have 1, and that's 2 over 1. So that 2 is just going to pick up a factor of x minus 1. So it's going to be 2 times x minus 1. And then when you work that out, you're going to get 1 plus 2x minus 2 over x minus 1. When you get it in its polynomial form, you've got 2x minus 1 over x minus 1. And so this is how you're going to state your asymptotes right here. You're going to use that And the horizontal asymptotes, you're going to follow those cases. This is case 1, case 2. The numerator and the denominator have the same degree. They have the same degree, then your horizontal asymptote is found by looking at your leading coefficients, 2/1. So you have y equals 2 is going to be your horizontal asymptote for this graph. And then your vertical asymptote is found when your denominator cannot equal 0. So you're going to go back up to this one. 2x minus 1 over x minus 1. Looking at the denominator, you have x minus 1 equals 0. Solve that figure out what x is equal to by adding 1 to both sides. You get x equal 1. So x cannot equal 1 because that's what's forcing your denominator to be 0. You plug in 1 here, you're going to get 1 minus 1 is 0. So your vertical asymptote is going to be at x equals 1. And that's how you would state your asymptotes. And then I hope that helps. This graph only has one horizontal and it only has one vertical asymptote. And they're right here in this graph here. There's the horizontal one at 2 and your vertical one at 1. And then all these other points are found by just plotting. So if I want to get the behavior of the graph over here, then I would just pick up points over here. What about 2? And I'll plug in. I can use this graph, but what I was finding is that it was a little bit trickier to plug the points in. So I just preferred using this one to plug the points in. So this one, and so y equals 2x minus 1 over x minus 1. This is the same function. So I would rather use this one. So if I want to see when x is 2 here, I'm anticipating it being over here somewhere. But I would just say y equals 2 times plugging in 2 for x minus 1 over 2 minus 1. And then evaluate that to find out what my function is doing when I erase my table. So I didn't mean to do that. Well, when x is 2, y is going to be 2 times 2 is 4 minus 1, just 3. 2 minus 1 is 1. It looks like 3. It's a good solid points there. So we've got 2,3 on the graph right there, which we kind of already suspected. 2,3. Let's see what's going on at 3. Hopefully that's helping. Oh, you're welcome. All right, so what I'm going to do is I just realized I'm over on my live stream. So if you don't have, wait, what's the 3 mean? Oh, you want me to do 3? I'll do it real quick and then we'll stop. So when x is 3, I'll do one more. Stop. Y equals 2 times 3 minus 1 over 3 minus 1. So this is going to be 2 times 3 is 6, minus 1 is 5, and 3 minus 1 is 2. So this is going to be 5/2. That's 2.5. So at 3, we're at 2.5. So we've got this thing going on. I suspect it's going to be doing this. And of course, you do have Desmos and you have these graphing features, but I want to sketch them by hand without the use of technology. Because you never know when your calculator batteries are going to die. Mine died in the middle of my live stream. That was tragic. But I have more batteries and I can charge them. So, all right, very good. And that was a really good workout for me. So I really appreciate that. And you are very welcome. I am still going to be working on these rational functions again tomorrow, probably. But I do want to make sure that I make it back eventually to the trig. So we'll just see. I'm just trying to play it by ear and informally, do math. So again, thank you so much for watching my videos, and I will see you again tomorrow. Bye.